Okay. So this is kind of just an application of uh, the table I gave you of all the simple shapes, but you do have to do some kind of mental turning around of things and whatever. So what I gave you for the semi-parabola shape was, if this is A, and this is H, the centroid this way is, I think, 3/8. So 3A over 8. And then the centroid this way is 3H over 5. Does anybody have that list in front of? I guess maybe I have it right here somewhere. Probably worth making sure that's right. Okay, so 3A over 8. Yes, 3H over 5. Okay, and then the area is 2AH over 3. All right, well, I'm going to draw first the free body diagram with that distributed load in there. Whatever, that looks terrible. Worst parabola ever. And then the other loads, this has a mass of 1,500 kilograms, good Lord. So there's a weight of 1,500 times 9.81, which is 1,4,715, I think. And then we have a fixed joint with the ground, so this is R and then a couple M. And now, in order to represent that distributed load as a point force, we have to use the shape information. We don't care about the vertical location of that centroid. All we care about is the horizontal location. And this thing is flipped sideways. So if H represented the height before, you can think of like this width now being that H. And so this distance is 3H over 5. And H is equal to 5. So this is just equal to 3. That's convenient. And then the area is 2 times 15,000 times 5 divided by 3. So 150,000 divided by 3. So that is 50,000 newtons. And so now I'm going to draw a new free body diagram. You don't have to draw multiple free body diagrams once you feel comfortable with this. That's fine with me. I'm just going to do it at least for now while you're sort of getting used to this process.
Professor,
Yeah.
if the height of the load is, well, we don't know the height of the load, right?
The height of the
Parabola, distributed load.
Yeah, well, really the height is just a representation. I mean, the height that it's acting is on the surface of the thing. That's why the vertical point of that centroid doesn't matter.
I'm just a bit confused. Why are we using the area of the parabola?
Because the area is the total point force. The area of that shape. I mean, you can think of it like this. Like df dx is equal to whatever that shape is, And so the total force is the integral of this dx. So that's why, all we're trying to do is calculate the area of that shape to give us what that total point force F is. And so we still have this weight force at the center. We still have these reactions from the joint. And then we have a downward force of 50,000 newtons acting at a distance of 3 meters from the end. This is 3. Any other questions about that? So now, what am I going to choose as the about point? I guess I'm going to do it here. So rho, force, moment. I'll do the reaction force first. So that is at a location 4, -0.2. The force is Rx, Ry. The cross product is 4Ry plus 0.2 Rx. Then we have the couple. For the couples, we don't care about these. Then we have the weight force. The location there is, the whole thing is 5, so this is 2.50. And the weight is 0, -14,715. So that is negative 36,787.5. And then the last one is the distributed load. That row vector is 3, 0. The force is 0, negative 50,000. And so the moment is negative 150,000. Newton's second law, Rx, Ry plus 0, negative 14,715 plus 0, negative 50,000 is zeros. And the moment equation says I'm rearranging a little, 0.2 Rx plus 4 Ry plus M is equal to negative 186,787.5. And you could do that by substitution. So R is equal to 0 for X, 64,715 for Y. And so M is equal to I got negative 445,648 Newton meters. And the negative means that's a clockwise moment. Yes. Thank you. That's why I don't usually cut corners like that, because I always make a mistake. So, well, I guess that changes the answer a little bit too, doesn't it? So the answer then is, this time I got negative 72,072.5. Yes.
Can you do number 6?
Sure. All right, so free body diagram looks like this. We have a force vector here. I'll call that RB. And then a force with a known direction here. I'll call that RA. We're ignoring weight. And then there is a distributed load like that. That's everything. So now we'll figure out the centroid and the magnitude of this distributed load. The centroid is a third of the way, a third of the distance from the edge to the point. The total length of this distributed load horizontally is 0.5. So this distance is 0.16 repeating. And then the total force is the area of that triangle, which is the base times the height. So 0.5 times 10,000 divided by 2, so 2,500 newtons. And if I redraw that free body diagram, we have a downward force of 2,500, and it's acting 0.16 repeating from the left end. I am going to put my about point here. So first, let's see, the 2,500 Newton force. The row vector is 0.16 repeating, 0 for y. The force is 0, negative 2,500. So that is at 416. Yeah. Negative 416.6 repeating. And then the RA, that is, the row vector is 0.3 repeating, 0. The force is 0 RA. So the moment is 0.3 repeating times RA. And then RB, that is at 0.6 repeating, 0. The force is RBX, RBY. Moment is 0.6 repeating times RBY. So Newton's second law says RBX, RBY plus 0 RA is equal to 0 positive 2,500. And then the moment equation, 0.3 repeating times RA plus 0.6 repeating times RBY is equal to positive 416.6 repeating. I guess I'm going to write this out in an augmented matrix. We have 3 equations, 4 variables. I'm going to do RBX, RBY, RA. I don't know why I have RBX in there since we know it's 0, but so we got one of these zeros everywhere, then one RBY, one RA, constant is 2,500. Then RA 0.3 repeating, RB Y 0.6 repeating, constant 416.6 repeating. And I got RA is 3749.95. And RB is 0, negative 1249.95. Any questions about that?
Yeah. How did you find the distance of the force, 0.16?
Yeah. So we know that that point force is going to act at the centroid of that triangle.
Oh,
And the formula for the triangle says to go, the centroid is going to be 1/3 of the way from the edge to the point.
okay.
This whole thing is 0.5.
Oh,
So 1/3 of that is 0.16 repeating. Any other questions? Any other homework questions? I think I only gave you 3. Do you want to see the other one? The other one was pretty straightforward, I think. Yes.
can you just go back?
Down?
Thank you.
Yeah. Okay. So now I'm going to get into the next topic, which is kind of like, to me, the most important topic in this class, kind of the heart of this class. And that is structures. And a structure is a collection of rigid bodies connected by joints. So an example of this would be like say you have these 3 members connected by pin joints, and you have some forces applied. A roller down here. And the question is, what are the external loads on each one of these members? And you can imagine this is important for lots of like construction applications, also for, engines, treating the human body as a connection of things, so you can find muscle forces and joint forces and stuff. There's a ton of applications for this. The way you usually see this in statics textbooks is, so usually textbooks break this up into 3 separate topics. So they break structures into trusses, frames, and machines. And then the approach you use is different depending on which of these kind of things you have. So the approach depends on that classification. There is a benefit to this way of doing it, and that is that it optimizes the number of equations and variables you have. So you don't have to solve systems of as many equations, as many variables. The drawbacks to this approach, though, is first, you have to categorize it correctly, or else your answer is going to be wrong right from the start. You never have a chance to get it right. So you have to classify correctly to get the right answers. And then second, there are statically determinate structures that don't work for any of these 3 approaches. So, like, there are structures that are perfectly solvable using statics, but these methods can't solve them. And so I'm going to sort of emphasize a different way of doing this. I'm going to just give one single method that works for every structure. So you don't have to worry about classifying them. And there are no structures that are statically determinate that this can't solve. The downside of that is it can produce a lot of equations and a lot of variables. Okay, well, to me, when these textbooks were written 75 years ago or whatever, like a long time ago, having too many equations and too many variables was a really important problem, because people had to do these calculations by hand. Things are very different now that you have reduced row echelon form available. You can, use MATLAB to solve these big systems of equations. So it just isn't as big an issue as it used to be. So I'm going to do this thing where we're going to get, often big numbers of equations, big numbers of variables. After we're done with this single method that works for everything, I am going to go back and talk a little bit about the truss simplification and some of these other simplifications, just so you've seen it or whatever. But to me, I think the way to go probably is to just use this single method all the time. Then every time you do it, it reinforces it. You don't have to learn 3 separate approaches. Whatever. So I guess the way I'm going to do it, because really this method just comes out of the rigid body stuff we've been doing. So I'm going to just jump right into an example problem. I'm going to do that before I talk about the method. And then next time I'll give you like sort of a step-by-step method that is what I did on this example, but you can sort of see, follow a set of steps to make it work. So I'll start with an example. Let's say it's pretty similar to the one I just drew. So let's say we have this equilateral triangle. Instead of 3 members and a connection to the ground with a roller, this is just 2 members and they're both connected to the ground with pin joints. And let's say we have a 6,000 Newton force applied to the pin that connects the two. And let's say that all of the lengths are 1 meter. And then let's give these things masses. So the mass of each member is, let's say, 20 kilograms. And we want to calculate the external loads on each member. So the way I'm going to do this is I'm going to name these each body. I'll call this body 1 and this body 2. It doesn't matter which you call which.
Members, like that, just like bodies?
Yeah, that's right. And then I guess I'm going to name these pins. I'll call this pin A. Pin B and pin C. And I'm going to assume that at each pin, the members touch the pin, but they don't touch each other. Okay, so now I'm just going to go free body diagrams for each of those 2 members. One thing I'm going to do is, so I'm going to be very specific about what I'm including when I isolate each body. So for my free body diagram of member 1, I'm going to isolate member 1 along with, so lumping it in with this body, the pins at A and B. Okay, so the pin is at each end is part of my what I'm treating as member 1. Okay. So what forces are acting? There's a downward force of, this is the weight, 20 times 9.81, so 196.2. And then what's the force that the ground applies to that pin? That's just an unknown force vector. That's just following the rules of pin joints. I'll call that RA. And then up here, what's the force that member 2 applies to that, applies to that pin that we're treating as part of member 1? That is also, it's just the force applied by a pin joint. So this is just going to be an unknown force vector. And I'm going to use that subscript notation to name this. I'm going to call this the force on body 1 by body 2.
And how do you know it was like that way?
The directions? Well, with a pin joint, you don't know anything about the direction, so we're just going to assume that there's an X and a Y component, and we'll just have to solve for both of them. So I'm just drawing those in the directions of the coordinate axes. And it, so we'll think about that when we get to it, But yeah, right, that member 2 is also connected to a pin joint, so we're going to think about it the same way. Okay, and then this 6,000 Newton force is applied to the pin. But that pin I'm including as part of my member 1. So I'm going to put that in this. Okay. Any questions about that? That's all the loads acting on member 1 if we include those 2 pins along with member 1. And now I'm going to go row force moment. I'll put my about point down here. This is an equilateral triangle, so that angle is 60 degrees. So I'll start with RA. Row vector is 0. Force vector is RAX, RAY. Moment is 0. Then we have the weight force. The whole thing is 1 meter long. So the distance from A to where the weight is applied is half a meter. So that's half a meter times cosine and sine of 60 degrees. So that is 0.25, 0.433. Just 0.5 times cosine and sine of 60. And the force vector is 0, negative 196.2.
Can you go up a little bit so I can see where the angle is?
Well, since these are all the same length, it's an equilateral triangle, so it's 60 degrees. So the angles are the same. So negative 49.05 is the moment. And then I'll go up to the 6,000. The row vector is 0.5, 0.866. The force vector is 6,000, 0. And so the cross product is negative 5196. And then last is that force F12. It has the same row vector. The force is F12x, F12y. Notation gets a little messy, and the cross product is 0.5 F12y minus 0.866 F12x.
Professor,
Yes.
how did we get the position for MG and 6,000?
Well, one thing you can do, I mean, we know that it's right in the middle of that.
Yeah.
But one thing you can always do, this always works. I don't know if any of you have ever thought of it like this before, but if you can come up with the coordinates of 2 points, the midpoint between them is just the average of those 2 points. So you can think of it that way, like the coordinates here are, 0.5, 0.866. Coordinates here are 0. So this is just half of that. That always works for midpoints.
So
You can always average coordinates to get midpoints.
because it's equilateral, the angle is 60?
60, yeah, that's how I did it. 0.5 times cosine and sine is 60. Okay, so now we're going to write out Newton's second law and rotational. Since we're sort of out of time, I'm going to just quick write this down as 3 equations. So Newton's second law and rotational Newton's second law gives us this. A first equation that says RAX plus F12x is equal to negative 6,000. A second equation that says RAY plus F12y is equal to positive 196.2. And then a third equation that says, if I rearrange, negative 0.866 F12x plus 0.5 F12y is equal to positive 5245.05. Okay, so if this was a rigid body problem, that would be the end of it. But let's think about the number of variables we have and the number of equations. Variables, we have RA, X and Y components, and F12, X and Y components. So that's 4 total variables. And we only have 3 equations. So we can't solve anything yet. Okay? But the next step is, now we're gonna set these 3 equations aside. We're gonna go to member 2, calculate the equations, the 3 equations we get from that. And what we'll see is that now we have 6 equations for 6 variables, and we can solve the whole system. Okay, so I'll do that next class. Okay, go away.